thank you very much, Gordon, for this introduction and for allowing me to present some of the work that we are doing in Bristol, but actually some of the work Gordon has also been involved in, focusing on reconstructing terrestrial temperatures in the geological past. And when I talk about the geological past, I mean probably slightly different time scales, although yesterday we had some really ancient talks about very ancient rocks, but today was mainly focused to the Quaternary. We're going to go a bit further back in time to the Eocene, Oligocene, and even a bit of Paleogene, actually. So focusing on organic geochemistry. So what I want you to take away from today's talk is that organic geochemistry is an awesome tool to reconstruct terrestrial temperatures in the past. But before I dive into the science, I just want to start with actually explaining a little bit of the context, like why is this important? So this is an image from the IPCC report, currently still the latest IPCC report, although the other one will come out pretty soon. And this is a cartoon showing all the different aspects of Earth's system where we have observed changes over the last 50 years. So think, for example, about the sea ice area that has declined over the last few decades. We know, of course, the composition of the air, especially the amount of CO2 and methane, has increased significantly, etc. Right? So for the modern day, we have quite a good, clear picture. We know lots of things that are happening because we have fancy satellites, we have Argo floats, we have lots of weather stations. We have quite a good idea what's happening in the modern day, right? But when we go into the paleo world, the picture becomes a bit fuzzy, right? I mean, and that's what lots of people in today's talks and in yesterday's talks have actually been trying to do, actually shine some light on some key aspects of the past, right? And in the past, probably 40 years, a lot of research has focused on marine temperatures. So if we look into the paleo world, we have quite a good understanding of marine temperatures, at least for, let's say, the last 65 million years. Composition of the air is also quite well constrained, especially for the bit where we have ice cores. But even for the last 65, maybe 100 million years, we have quite a good understanding of what CO2 did. But some other key bits of Earth system we don't understand very well. And one of them is temperature on land. And that's what my research is focusing on, reconstructing temperature on land, finding new methods we can do it and then applying them. You might ask yourself, well, if nobody has focused on it so much, although I'm aware a lot of people in this meeting have focused on terrestrial temperatures and other aspects. Maybe it's not important, but actually terrestrial temperatures are very important and they control some key aspects of Earth's climate system. Think, for example, about the terrestrial biosphere. Temperature has an influence on that. You think about biogeochemical cycles. So here on the right-hand side in this graph, you see temperature on the x-axis versus the flux of methane out of like wetlands and rice paddies on the y-axis. And what you see is like when temperatures are increasing, we see an increase in the flux of methane. So when you increase temperature from 20 to 30 degrees, you sort of see like a 5 times increase in the flux of methane, right? Which is a very powerful greenhouse gas. Temperature has an impact on soil respiration rates, surface albedo, the hydrological cycle. Think about the monsoon, which is basically all driven by the temperature difference in temperature between land and the ocean, and land-ocean coupling. So the main thing here is that terrestrial temperatures are a key aspect of Earth's system. We just don't really understand very well how they operate, especially when we go back on timescales of tens of millions of years. So that's what my research is focusing on. And specifically, I focused on reconstructing organic geochemistry, so biomarker proxies, specific for peat. So you might wonder why peat. Well, peat actually has a number of advantages. First of all, peat can be found across the globe, basically everywhere where you have enough water, you can find peat. So we have peat in the tropics, in the high latitudes, mid latitudes. I mean, a lot of the UK was and still is covered by peat. Another main reason, and especially for an organic geochemist like myself, is that they're very rich in biomarkers. So we don't struggle for material. We have lots of material. But also very important is that peats are often preserved as lignite or coals, and they are mined in lots of places, especially in the Northern Hemisphere. So it's actually quite easy to access a lot of these sections. We don't need fancy drilling campaigns or marine vessels. We can often just hike up to mines and go sample there with some appropriate permissions and safety equipment. Also important, and for some details later on, is that most biomarkers you find in the peat are produced right there in the peat. They didn't transported there by rivers or something. That might be a problem with, for example, marine sediments. Sorry. And peatland is also crucial for terrestrial biogeochemistry. Think about methane. So if you can constrain the temperature aspects, we can actually then also start to understand what actually implies for biogeochemistry. So peatlands are quite a good archive to go for. And the lipids I'm going to look at are called branched glycerol dialkyl glycerol tetraethers, or branch GDTs for short. And branch GDTs come in lots of different variations. I show here the main groups, but there's lots of different ones. And it might look all different for the non-expert, but actually the main thing that can change is that they can change the number of rings. So they can come without rings or with 1 or maximum 2 rings, or they can change the number of methyl groups. So they can have, for example, 4 methyl groups. You can see here in the left corner, here has 4. They can have 5, the pentamethylated, or they can have 6, the hexamethylated, right? So the main thing is that these lipids, which are produced by bacteria, can change the number of rings and the number of methyl branches. And today we're mainly going to focus on these variations in the amount of methyl branches. And the reason is that there's a lot of work done led by the Naafs, sort of like 10, 15 years ago, when they looked in mineral soils, so not peats, but mineral soils, and they looked at the distribution of these branch DDT lipids. What they saw is that a tropical soil, for example, here on the left side, you see a soil from Nigeria, looked very different in its distribution from a soil from Iceland, shown here on the right. Nigeria warm, Iceland being cold. And what you see in these warm soils, you see that most branch GDTs come in this tetramethylated form, so they only have 4 methyl branches. Well, in these colder soils, they have 5 and 6 methyl branches, right? So what they propose is that this degree of methylation, which can be captured into an index called MBT, is correlated to temperature. And in 2007, they published this paper where they showed MBT is linearly correlated with temperature. So this was for mineral soils, and actually some of the early work suggested that this didn't really work in peats, but this was all quite limited. So what I set out to do around 5 to 6 years ago, funded by an advanced ERC grant awarded to Rich Bancroft, was actually try to see whether we see a similar relationship in peatlands. If you actually bring a global database of peatlands together, do we actually see this correlation between the degree of methylation of branch EDTs and temperatures? So we collected samples, or mainly I collaborated with people that collected samples from all over the world, and we basically have a modern peat database that contains samples from every peat-forming environment on Earth, from the tropics to the high latitudes, from very acidic to alkaline peats. And in all these peats, I measured the distribution of branch EDTs. So this was around 470 samples in the end that we analyzed, and plotted that against temperature and see if we can see this correlation where the degree of methylation varies with temperature. So here we can see MBT. And now since 2007, things have changed a bit. So MBT is now called slightly different. It's called MBT 5-methyl prime. And we can talk about what that actually means if you're very interested. But basically, it still reflects the degree of methylation of these branch DDTs. And here we have temperature on the y-axis. And when we look then at the distribution of MBT in peatlands, we can again see this linear correlation between the degree of methylation and temperature. Now, there's still a bit of scatter. For example, the error bar here is around 4.5 degrees, so that's relatively large. So maybe this method is not ideal if you want to reconstruct the little ice age, for example, or smaller events. But here we mainly want to look at bigger variation, bigger temperature variations. It's also important to remember, though, that this error here is a calibration error. It's a spatial error, an error. While within one peatland, while a lot of the variations that lead to the spatial area stay constant, the downcore error is significantly lower. So we have this calibration, MBT with temperature, and we see this in peats, we see in mineral soils, but actually what we were then wondering was what is actually driving that? What does this actually do to a bacterial membrane when you change the degree of methylation? So to sort of get a physical and mechanistic understanding of this proxy, I worked together with enzyme modelers that built models of membranes of for example, bacterial membranes, and this work was led by Sofia Oliveira, who is a postdoc in Bristol. And what she did is she built membranes in computer simulations consisting of different branch GDTs. So here you can see an example of a membrane where all the blue dots is water. So you can see water on both sides, and then in the middle you see this membrane consisting of branch GDTs. In this form, and in this simulation, it was the hexamethylated branch GDT. So we did simulations for lots of different branch GDTs with different number of rings, different degree of methylation. And then we looked at some key aspects of the membrane. For example, we looked at the area per lipid for these membranes, which tells you something about the packing density of this lipid. Or looking at the maximal thickness of the lipid, right, which tells us something about the membrane packing. And what you can see is that there's clear differences. So the unmethylated lipids shown called 0M0M because they have no methylation. Those look very different from the hexamethylated lipids that are named 3M, 3M. And also in between, you can see sort of like this increase in area per lipid as you increase the degree of methylation, while the maximum thickness decreases. And we looked at lots of other parameters as well. And collectively, what this showed us is that when you go from unmethylated lipids to very methylated lipids, you see an increase in membrane fluidity, but you see a decrease in membrane order. And that actually starts to make quite some sense if you think about it. So if you're a bacteria growing at a very high temperature, you want to have a low membrane fluidity, but a very ordered membrane, right? To stay compact and don't lose your membrane integrity, right? Well, if then temperature decreases, your membrane would solidify. So what you do is you start to make your membrane more fluid. Yeah. So based on this work, we now actually have a mechanistic understanding behind these empirical observations that the degree of methylation is correlated with temperature. So we now have a mechanistic understanding underlying our foundations and our calibration. So the next step was then to actually apply that. And we are applying this throughout the Cenozoic. And I already saw this graph coming up yesterday as well. Somebody presenting, this is a recent compilation by Thomas Westerholt and others, compiling basically the evolution of global climate and the global carbon cycle over the last 68 million years. And we are here on the right at 0, and this is on the last 68 million years ago. And today I'm just going to show some examples of how we can apply this new proxy based on peace, apply it to lignites, and tell some fundamental aspects about how Earth's climate system was operating in the past. So first I'm going to apply it to the Eocene-Oligocene transition, when for the first time large ice sheets appeared on Antarctica. And then I'm going to briefly show you some results about the application to the Eocene hyperthermals, such as, for example, the PTM, which is the warmest period of the last 65 million years. These events where we have large perturbation of the carbon cycle, lots of carbon into Earth's ocean atmosphere system, maybe coming from methane hydrates, for example, though there could also be other sources. Lots of warming, ocean acidification, and we're going to see what that actually did to temperatures on land. And this is lots of work that's done by my postdoc, Victoria. And the first one was the Eocene-Oligocene boundary. So during the Eocene, we had this greenhouse climate, and we had this gradual cooling. And then at the Eocene-Oligocene boundary, we had sort of like that step change at the EOT, where we suddenly go from an Antarctica without ice sheets to Antarctica covered by significant ice sheets. Whether it looked exactly like this, like the modern day Antarctica, that's not completely clear, but we had significant ice sheets on Antarctica across this boundary. And we have lots of marine records that cover this period, but actually very, very few, or actually basically no terrestrial records. So we collaborated together with people from the University of Melbourne who have lignite samples that span this Eocene to Oligocene transition. And here you see the sequences. So we have lignite seams from the middle Eocene, from around 40 million years ago. We have the late Eocene, the very latest Eocene, and then the earliest Oligocene. And we actually have the EOT boundary here, although that's not in a lignite, but we have the transition here. And in all these lignite samples, we applied a calibration to reconstruct temperature based on the branch GDTs. And what you can see is like this gradual decline in temperatures from pretty toasty 27 degrees Celsius during the middle Eocene to 24 degrees, and then 22.5 degrees during the latest Eocene. And then we have this step change across the EOT where we suddenly get temperatures around 20 degrees. So we have this step change here of around 2.5 degrees cooling. So the question we had was then, what could actually drive this cooling? So we collaborate together with a number of climate modelers we have in Bristol to see if we can look into different simulations and see which simulation actually best fits with our temperature proxy. So what you see here on the left is the distribution of the temperature proxies. So this is like our proxy reconstruction, which shows on average we have a temperature decline of around 2.5 degrees. And now what you see on the right is different simulations where different boundary conditions were changed. For example, in these simulations with ice only, they put a big ice sheet on Antarctica. And then we looked at what does that do to the temperature at our site, which is located in the southern part of Australia, right? And what you can see is that simulations that go on ice sheet or that change the paleogeography do not at all lead to a cooling as we see in the proxy record, right? So just growing an ice sheet on Antarctica doesn't cool southern Australia. And changing in paleogeography also doesn't do it. Actually, the only way we can get a significant amount of cooling is if we decrease CO2. So in these simulations, CO2 was decreased by 50%, and that gives us cooling of around 4 to 5 degrees Celsius. Now, the cooling we observe in the proxy record is actually half of that, roughly. So probably CO2 only declined by around 25%, which is also consistent with some of the rough estimates of CO2 we have for that period. But basically what these simulations show is that the only way we can reconstruct our proxy data is if we decline CO2, meaning that CO2 was a main driver in the Eocene-Oligocene transition, because of course declining CO2 is also a really good way to actually build an ice sheet. And this paper should come out in the next few weeks in Nature Geoscience for those that are interested. So that's the EOT. We can then even go further back in time to the hyperthermals of the Eocene, and this is working together with a lot of colleagues from Germany and from Canada, looking at lignites we have from Ellesmere Island, high up in the Canadian Arctic, just next to northern Greenland. And there again, we have lignites that cover some key periods of the sinister climate. We have these hyperthermals. So here we have the PTM, characterized by these very negative carbon isotopes. And we have ETM2 here, so this is the next hyperthermal, and we probably have an even smaller hyperthermal here that I forgot the name of. But the next one, we have that too. And in all of those, we reconstruct the temperature. So this is the temperature we're getting, and I know we're almost out of time. So I'm just gonna go through this. Basically what you see is that we see that in the Canadian Arctic, at places that currently look like this, and during the Eocene, these locations were still pretty high up in the Arctic. We see temperatures of around 15 to 20 degrees during the PTM, slightly cooler during the earliest Eocene. Again, rapid warming of this beautiful onset of ETM2, temperatures to, again, between 15 and 20 degrees, slightly cooler, and then we see the beginning of the warming into the eco. And we're currently looking into what this actually means for example, the methane cycle in these high latitude wetlands during this time. So these are the take-home messages. I'm just going to leave them up here because of time. Then we have time for maybe 1 or 2 questions if people have them. But the main thing I want you to take away from this is that organic geochemistry is a very powerful method for reconstructing temperatures in the past. And I want to end with thanking all my co-authors and people that helped with collecting samples, analyzing data, and you for your attention.
Cool. Thank you very much, David. Super cool to see what you've been up to, especially the modeling stuff. That is pretty neat. Are there any questions in the chat box? If not, then I have many, unsurprisingly. Okay, I guess just one, which is a little bit of a tangent, but with the molecular modeling, you've been looking at the branched GGTs. I suspect you have also been looking at the isoprenoidal compounds from Archaea. Do they also fit into that narrative of changing their structure at higher temperatures?
Yeah, no, it's funny because, I mean, we got the reviews back a few months ago for this paper as well. And they said like, oh, can you also look into this and this and this? And actually, doing this simulation actually is really a lot of work, especially for the branch ETs, because nobody had ever built a membrane of branch ETs. So actually just building the membrane itself actually takes a few months of work because you have to parameterize every lipid by hand basically. So Sophia spent a lot of time on this. So we haven't looked at the ISO yet. I mean, there are some. I mean, there are some simulations for ISO GDTs already, and they show that like changing the degree of methylation on ISOs has a similar impact. Also, changing the degree of cyclization has. So there's some work for Archaea's already done there, but we're currently starting to think about actually doing other simulation, maybe with 5 and 6 methyl branch GDTs and etc. But it's actually a lot of work doing these simulations. And what I showed you, that's actually all the work we have done. And because that already took a lot of time. That's basically the lockdown project, because that could all be done remotely.
Yeah.
But yeah, it's good. I mean, it would be really cool to see like what does it do to add. I mean, methyl GDTs. Everything. There's a lot of cool stuff to be done. We just don't have the time yet.
Yeah, that's very cool. And I wasn't the reviewer, by the way.
Oh, good.
Kind of sounds like I was. Is there any other questions from the floor?
Too much organic geochemistry.
Not enough. Not enough. Okay. Well, since we're just about at time, we will finish there. Thank you again, David, and thanks to all the other speakers in the afternoon session.